So, hello everyone. In the last class of this machine learning for image processing course, we were discussing first about the contents of the course with the help of different modules that have been drawn, or a block diagram that have been drawn for solving the classification problem. Then we started an introduction to image processing as machine learning for image processing. We wanted to take a look at image processing part to begin with. So then we have discussed when can an object be imaged, how can it be imaged, and two important phenomena from the signal processing point of view that happen when you are creating a digital image of a given object. What were those two phenomena?
Sampling and quantization.
Very good. Sampling and quantization. So in that, we had a brief discussion about the sampling part. So essentially, your sampling should take care that there is no aliasing happening when you are either acquiring image or the downsampling your image. So for that, what did we see? One way to look at it is assuming that your signal is band limited signal. Nyquist theorem is something that give you an idea about the frequencies there. Just maybe as an extension of that, let me pose one question to you. Suppose you know that you need to downsample an image below what actually your Nyquist theorem is telling you. So in that case, how do you downsampling you how will you downsample your image while still avoiding any aliasing? How do you do that? You know that you are going to down see, look at my snapshot of my image here itself. Okay, you want to downsample it. Let's say when you downsample it below a particular point, you will obviously see a lot of artifacts. Assume that that would have been much clear if I had shirt which is having, let's say, stripes, close stripes are there. Okay, suppose if you are downsampling that image below a particular point, you'll see good number of artifacts. Same could be the reason if there is some other background than plain background where you could see lot of textural or frequency variations. You still want to downsample your image, okay, but you don't want aliasing to happen. How do you address this problem? To simplify things even further, what is the pre-processing that you do before downsampling such that you can avoid aliasing that is coming due to downsampling? Hmm.
We can remove the high frequency components, I guess, before downsampling
Right. How do you remove the high frequency ones?
by passing through a low pass filter.
That's all. You do a low pass filtering and then you do the downsampling. When you are doing any machine learning stuff or a deep learning stuff, you are applying an image, this background should always be there. It is not that you just blindly apply something. So to highlight that, just I wanted to add this auxiliary point to it. Okay, anyways, coming back maybe for the sake of completion, let me talk about quantization also here. Then I'll come to the math part of it. What we meant by quantization that we come across in an image is the number of bits that you would use. So the size of the grid has been dictated by your sampling. And of course, then 1 pixel here would be equivalent to so much of or micrometers of distance there. But after that, at each of this pixel location, you need to store some intensity value. So the second effect of quantization is more about the number of distinct intensity values that you could represent. In other words, suppose I am using just 1, 2, 3, 4, this way of integer values. Then what would happen if I have 2.1, 2.2, 2.3, 2.4, maybe all these things I would put under 2. So that's the kind of quantization I'm doing here. Anything more than 2.5, I would put in the basket of 3. All of those values would go there and would represent them as if it is 3. Now, it is more now about how many distinct values I would be using in an image to represent these intensity values. Assume that I would assign a single bit to store the intensity values here. Okay. Assume that I have an image of size m by n and I'm going to use a single bit. Then what would happen? This is where you end up. This is, let's say, if I'm not wrong, maybe this could be the X-ray scan, as it is just one way, or it could have been also a CT scan where you are taking just one sagittal view. By the way, this view is called a sagittal, one slice of that. This could be anything is possible. Okay, why do you take a scan, for example? You want to distinguish different regions in the brain and see them and notice if there are any tumors or tumor. I am telling it because you are seeing there the head. Had that been lungs, some abnormality, some infection, these kinds of things are there. If at all it is something is there, that's why you want to see. And within that image, you want to see a more distinction, or this is also sometimes you would refer to as high resolution. Resolution here is in terms of number of rows and columns. Here the resolution is in terms of, this is a general word, resolution. It is used in different contexts. Sometimes this is referred to color. So you have to be clear on to which this resolution is referring to. Here, when I say resolution, this is about the distinct intensity values that can be represented. And if you use more, as you keep on increasing the number of bits to be used, you could end up with a scan like that. So which is it that is desirable? Of course, depends on what is your objective there. You want to see something, some assume that there could have been an injury to the skull. You want to see, this is the skull bone, let's say here, this is what you see, is the skull bone here. Then one kind of resolution would be good enough for you. Okay, again this is and then, for example, anyway you want to see something inside this brain. If some clot has happened, you need it at a much higher resolution in terms of distinct intensity values that you can represent. This is what we refer to as quantization. This is quantization of intensity values to be stored at each pixel location. My question is, assume that I am using a single bit of information here at each pixel to store the intensity values. Then for an image of size m by n, how many bits will be required?
M into N.
Very good. Okay. See, for example, in these images, these images, they are using 1 bit, 2 bits, 3 bits, 4 bits, 5, 6, 7, 8 to store the intensity values. Good. Then the subsequent question, if I am using a single bit to store the intensity values, how many distinct intensity values can I represent?
2.
Right, very good. Now let's come to this case. Now I use 2 bits now for storing an intensity value. How many distinct intensity values can I represent here?
4.
4.
Very good. So if I use 2 bits, 0, 0, 0, 1, 1, 0, 1, 1, right? This is equivalent to an intensity value of 0, 1, 2, 3. So what is the, suppose now, I would like to generalize this now. I use L bits, okay, to store the intensity values at each pixel. I would be using L bits. How many distinct intensity values can I represent then?
2 power
If
L.
I'm
Power L.
very good, 2 power L. Good. Now, next question. What is the maximum intensity value that I can represent?
2 power L minus 1.
Very good. 2 power L minus 1. Maximum value is 2 power L minus 1. And minimum value is
0.
0. Right. Now, the next question. For an image of size m by n, how many bits would be required now?
Mn into L.
That's all. Mn into L. Right? Mn times L number of bits. Okay, assume that this number is big. I want to say it in bytes. So how many bytes? Can you say that? Bits in
MNN by
bytes.
8.
MNL by 8.
That's all. M by n by 8. Okay. Let me call it with some x. I want to say it in kilobytes now. How much is that value? Okay, bytes you typically write capital B, bits you might write small b. Now I want to represent in terms of kb because that number also become pretty big with increasing mn values. Okay, that number let's call 1/8 of m times n times l is some x bytes you got it. Now kilobytes, how do you represent that?
X by 2 to the power 10.
X or
2
X
power
over
10. 2 power 10.
what is that?
1024.
Correct. That's it. 1024. Right. So this divided by, if I want to represent it in megabytes, I should further divide it by
1024.
that's how. That will give you in terms of megabytes of the size. And make a note here. This is a number we are mentioning when you do not use any compression while storing these numbers. Even there are two types of compressions, lossy compression and lossless compression. You could still retain these values without any. So how can you compress all these values? There are different, now these are just the information of bytes are there. Okay, there are different ways you can compress. For example, the same intensity bytes are getting repeated. You might have a coding, so Hoffman coding, something different codings you would have come across, right? So when you store it as a JPEG image, for example, if you calculate through this manner, and if you see 10 MB, for example, okay, 10 megabytes, but the moment you see the size of the image there, you go to the properties or even keeping your cursor there would show you that a 10 MB in this manner would still be shown as something like 1 MB or 2 MB. It is because there is a coding that you are using to store it in a more efficient way. But when you load it in MATLAB, just you load the image and then see the number there. If you can also, there is a way you could see how much memory that WHO or WHOS, I don't exactly remember. When you see it or some other command will tell you how much memory it is occupying. And this should exactly match with a raw image when you are not using any compression. Clear? Any question, or is that clear? Typically, as I was mentioning in the previous class also, this JPEG, PNG, TIFF, all these formats would be using 8 bits for storing the intensity values. Okay, 8-bit means what is the range of intensities now? 0 to, if you are using 8 bits, 0 to
255. 255.
right, 0 to 255 is the range of intensities that it would use. Again, although this is done in this manner, keep in mind that there is no hard rule that enforces you to use only 8 bits. For example, in medical imaging applications itself, particularly in CT, you could expect negative intensity values also. There, the negative intensity value has a meaning there. Of course, while displaying, the most negative you start with 0 and the highest with 1. Displaying values, don't get it confused with the actual intensity values, because as such 255 has nothing to do with the brightest. It is just the interpretation we do. Okay, it is not like even when you are acquiring an image, it's not like you will get there 255. You have a photo, a film that is sensitive to visible light. You kept an object there, light got reflected here. Don't be under the impression that it knows already that you will be using 8 bits and you will get 254, 255, all these numbers. You would do a conversion finally where the brightest would go to, assuming you are using 255, it will go to 255. The darkest would come to 0. Okay. There are imagings in the interest of time, and anyway, that is a different, altogether a different context. So we'll not go through that, but suffice to know here at this point that there are indeed applications where negative intensities does matter, but don't get confused on how do I display negative intensities. What does that really mean? Okay, just it is enough if you know, as I said, the darkest will be 0, the highest is brightest. Okay, typically it is not uncommon also, once you load the image and do some operations on that, you would use a range of 0 to 1 and do a lot of things. There are instances where you will do that. Okay, that is negative things. So when you are using negative things, you cannot store it with unsigned char. You would use, for example, signed integer number. Okay, integer will take 32 bits. First bit you would assign it to C, positive or negative. Let's say 0 is positive, 1 is negative. The rest of the digits you will manipulate with that. This you always keep in mind. Okay, are these things clear? Can I go ahead with further discussions? So now I will come back here. Okay, this is anyway covered now, but still for the sake of completion, let me tell that you are now a 2D image. Essentially, you are looking at it now as a function of m and n, just like f of xy in case of a continuous variable. Of course, if you want me to be more precise, anyway, I'm not planning to do frequency domain analysis in this course. Otherwise, this is what I would rather use to distinguish between continuous and discrete. Anyways, you can follow anything, but a image can be seen as a function of m and n or xy, whatever variables you give it, where m and n represent the indices of the image, and at those locations you have pixel intensities. Pixel comes from the word actually picture elements. You can call it image elements also, because those are the elements that constitute together an image. So picture elements have been shortened as pixel. So this is what you have when you load an image. For example, it does has, for example, if I have an m cross n image, when you load it and call your MATLAB, how is it stored, or any other most of these things? For example, let me use capital A here. Capital A equal to im load, let's say pepper.png. Some image is there, pepper image is there, I did that. Okay, so assume that. So how is this stored now? What will be the A? What exactly is this A now?
Matrix.
Yes. Can you tell about which dimensionality of that matrix?
In case of a gray image, it's going to be m by n, two-dimensional.
Very good. So in
Yeah.
case of a color image, it would be
It's going
m
to be-
cross n cross 3. So color image is nothing but you have 3 channels, red, green, blue typically. And again, it is not the only way an image is stored, although it is that way. So let me just hop here and there to, since we are just done the discussion, we are moving there. RGB is just one way. One channel is for red sensors coming out of that. Another is for green and another is for blue. That is not the only way. There are better ways. Those who had trying to choose some colors for your PowerPoint presentation, or even in the Word document would have seen there. There is something called hue, saturation, brightness. This kind of cone is there. Each has its own advantages. Again, these are only 2 that we are mentioning here. In fact, there are quite a few. Again, in the interest of time and other topics, we will not go into it. Otherwise, this is also a very interesting part of discussion. As I said, if it is a color image with m rows and n columns, it means it has typically, when you store these images, these are RGB, 3 are there. So then it is still a matrix, but a 3-dimensional matrix. And you would use the third index to access one of those 3 channels. Okay, even by the way we perceive things, we are able to perceive color, because in the whole setup, you have the sensors that can effectively capture red, green, blue are arranged. Okay, these sensors are arranged in a specific way on your back of eye in the retina. And that's why that light accordingly it absorbs. It's like putting a red filter. The rest that is what it is sensitive to. Okay, this is different anyways. Okay, that is what it is sensitive to. And that's how we are also indeed able to perceive the colors. And then we realized that world is after all not black and white. There is colorfulness to this world. And then we also started playing with color images. Okay, if we haven't had these 3 sensors implanted or present, we have not implanted, they were there, they were not there, we would have never known that world is colorful. Everything would have been a grayscale, and we would never have any colors to see. Anyways, that's just a comment on a side note. Coming back, these are just calculations we have already done now. This is assume you have an image of m by n, where you assume a square image. Okay, so let me just take some number in between. I'm picking up randomly. Suppose my image size is 256. So number of pixels I have is 256 by 256. Assume that I am using 4 bits to store the image, right? So number of bits that would be required is then will be so many number of bits will be required. These are the number of bits required. Okay, so yeah, 256 means this is 2 power 5, correct? Is that correct?
Yes, sir.
2 power 5 into 2 power 5 into 2 bits. This is 2 power 10 into 2. Sorry, I want to represent 2 bits, 2 distinct values. I need 1 bit here. So this is 1 here. Okay. This is 2 power 10 is nothing but 1024. And instead of 1, I use 2, just multiply it with 2. This is 2048. Right. 3 I am using, multiply it again one more time. So accordingly, you will see that into 2 power 1 it will come. If I am using how many bits are required, number of pixels is 2 power 10. Such things 3 are required, correct? So 2 power 10 into 3. So 1024 into 3 will be this one. Is that matching now? Yeah, 1000 into 3 is 3000. 3 times 24 is 72. Now in that way, let us see for this also. Suppose I am using a single bit, 256 into 256. That's 2 power 8 into 2 power 8. Okay, so into, for example, I am using 4, I want to use into 4 should give me. Okay, then you would figure it out. Just check these numbers. I could ask you give such size of an image, number of bits used, and could ask you how much memory it takes. Okay, right. So anyways, one more thing that one needs to keep in mind when we as humans process these images, and as a computer looking at these pixel intensity values, the moment you see, let's say, this part of the image, irrespective of whether you realized which part of the medical part it is, you would see it is very obvious for you that you will say this, there is a structure here, there is a structure here, there is a bright object here, there is something like this here, there is some contour here. This is all so obvious to you. You could realize from here that it's not just the intensities that we are looking at. We are looking at something else. What else probably made us interpret that image so quickly? The same thing, if you look at in terms of intensities, this is how it would look like. What does it made us infer this image so fastly? What else are we looking? It is not just pixel intensities that we look at. There are more things to it. Can you say
Maybe
at least?
maybe
Hmm?
orientation.
Well,
Orientation of the
orientation is one thing. That is a very specialized thing which will come a little later, but it's not even about orientation. Something else we are using there.
The edges.
Yes, correct. Edges are a very, very critical information. Not only edges, we would also see some texture, edges, contrast, the way it is varying, and sometimes we know some prior information also. That also comes to our mind when we are trying to interpret or infer these things all put together. So the message I want to emphasize here is that although we to begin with, we use intensities as the basic elements for all the algorithms, as we move on, we go towards something which is a better abstraction or a more efficient compact representation of that image also while dealing with the algorithms. For example, one of them could be edges. That's why in this course we would discuss about edges. Then you would see there is something else also. For example, it's not just edges alone. There are other ways of like representing in a compact as well as an efficient way. For example, histogram of oriented gradients is something that we would discuss. And those of you who are doing the DLCV course, they would deep learning for computer vision course. There you would see Harris corner detectors, then scale invariant feature transforms, SIFT, okay, that SIFT descriptor, classifier, and many other things. Perhaps you would have an opportunity to look at there. But so to rephrase it slightly differently, to begin with, initially, our features would be just the intensities, but later we would at least see one or two examples or instances where you need not necessarily give as features the intensities. You could extract from that a more high level features. Okay. Yeah, this anyway, this also is discussed already. This is discussed. And yeah, in any of one of these modules, for example, this image processing methods itself, we could go on and on for the entire semester. You would see image processing in itself is a course. And then once you go into it, for example, take the problem of image segmentation, that itself, you could give a course on that. Okay, there is no end to it. Nevertheless, we go and visit multiple places, then getting struck at a single touristic place, right? So in that perspective, we limit ourselves to maybe 6-7 classes, not more than that, for image processing, because we want to look at machine learning as well. In machine learning also various other topics. So the topics that we would discuss is, to begin with, we will start some pixel based intensity transforms, histogram based methods, spatial filtering methods that help you to, for example, do denoising of your images, extract the edge information and other stuff, and followed by that one method that lets you represent it with a better features for particular applications, that is histogram of oriented gradients. Maybe I plan to finish this off in 6 classes or so, 6 to 7, not more than that. Okay, so if any of you are interested, of course there are many sources available, many video courses itself are available. You can go through them out of your interest. Okay, even if you want to look at from some of my earlier courses as a part of medical imaging course, this is I'm talking in the course given in 2020. Later also the lectures were not edited. These are properly edited lectures, so they will be crisp. Most of them are, some are at least around 15 out of those 21 lectures are pre-recorded and then edited, so they will be crisp. Although they are 21, hardly they will be for 10 hours or so, I think 10 hours. We will now, with that, I'm done with an introduction to image processing, and then now it's time we start image processing itself. some methods. We start looking at it. We are done with initially course content, then a couple of classes, then one class on introduction to machine learning itself, and then an introduction to image processing so far. Now we start entering into the actual content. Of course, the earlier also you had some insights too, which is at a basic level. Now also we would see some basic methods for doing enhancement of the image in the spatial domain. So before I do that, since it's a logical break or a logical pause or shift of transition of content, do you have any questions?
Sir,
Yes.
you said negative pixels exist. Like
N-
we can study them, right?
Negative?
Pixels, pixel
Uh,
values.
yeah, pixel intensity values, for some reason, you may represent a negative value there, depending on how you are arriving at that intensity value.
And sir, when we load the image with negative intensities in the computer, will we observe the negative values or will we observe
No,
zeros and
see,
ones?
for your course, you will not come across that. If you are dealing with, if you happen to, for some reason, if you are dealing with CT images, there, see, if nothing has been mentioned about your image, it is very likely by default these images are unsigned character is used for storing these images. So when you are using unsigned, there is no sign information there. They are by default positive values. So you will get 0 to 255. In case of a CT image, these images comes with a header typically. DICOM is one format. There is HDR format, NIFT format. There are specific formats that will be used in case your image is having negative intensity values, and also your image size is not this 8. If it is something else, you would use a different types of formats like HDR, NIFT, DICOM, okay, .img, such different formats are there. In those cases, the header itself tells you what is the data type used. Data type could be even 8 bits, could be, for example, could be signed char or unsigned character. Okay, if it is unsigned character, then signed character means this is positive, negative, then you have to see from which minus to which minus. It can be, for example, it could be minus 128 to plus 127, minus 127 to plus 127 if it is using signed. So that information, unless that is given, you cannot interpret the data. In your normal this course, at least, unless you are using some medical imaging, that too CT images, you will not come across these negative values. Is that answering your question?
Yes, sir.
Hmm.
And
Any
sir,
further? Hmm.
one more question was that
Yes.
in this course, machine learning for image processing, is it similar to computer vision? Like, how are machine learning and image processing related here? Like, how will they incorporate each other?
Right. No, I think your question is a bit of a mix. You first part was you are asking about image processing versus computer vision. Then you are talking about machine learning and computer vision, like,
No, sir,
image
I was
processing.
actually asking that how are they incorporated in each other? Like, how is machine learning used in image processing, or how is image processing used in machine learning?
Suppose I am doing an image classification problem. Okay. So I have images. So if you recollect from the earlier slides, you could have a benign tumor and malignant tumor. Two possible tumors are there. You want your algorithm to distinguish between benign versus malignant. How do you do that? What you do is, now you would learn a pattern that would distinguish a benign tumor class from malignant tumor class. And that is where the machine learning is coming. You want to segment some objects here. You want to segment, these are the vertebral bones here on the back. So you want to get those segmentations. Now you give it a set of data sets where you have the segmentations available. Now the objective set for your machine learning algorithm is to learn the pattern that distinguishes or represents this particular part and find out its label, learn its pattern, and from that Do this when you give a new image. Same is the case with the denoising problem. Noise is getting added. You give a set of training data where you say that, look, this is the observed image. It should have been ideally this image, but this is the not because of getting noise added. This is what I got as an output. You let it learn the pattern of the noise or the pattern that converts your noisy image into a denoisy image. That's what your machine learning is done. This is for image processing. Okay, it's not image processing for machine learning. It is machine learning for image processing. So then you learn the pattern, and when a new image, a fresh image in your testing data comes, thanks to the pattern that it has learned, now it will give you, or expected to give you, a denoised image. Is that clear?
Yes, sir.
Good. This is a very important question, and this clarity has to be there for everyone. So even if anyone have any other question related to this, you would be required to do some basic pre-processing. Would be in many cases is required. It's not like you just dump your image directly to your machine learning. And some basic understanding is pretty much the domain understanding of image processing is required. And that is the reason why we are at least discussing few set of techniques, algorithms, which perhaps you might use as a pre-processing, or methods like histogram oriented gradients is one, where instead of feeding to your machine learning algorithm the individual intensities of each pixel, you could, for example, learn these high level features or handcrafted features, if you want to call them so, these histograms of oriented gradients. And it is this information perhaps you want to feed as an input to your algorithm. So that's why we are learning these things. Depending on the situation, the call will be taken. So in that perspective, the said we may go with just, we will very likely will go with just one exam. So I just wanted to clarify this, because this class committee meeting will be there. I don't know when, sometime in this week. So in that case, how do I plan to modify this weightage? Well, what I plan to do in that case is test 1, test 2, 20%, 20% I have given. If there is a single test, this one I would increase, that particular test I would increase by 10%, and the rest 5% I will adjust between the final exam and assignments. So it could be 30%, 45%, and 25% in that case. This could, your weightage could become. And again, I'll, depending on the situation, please allow me to change 5% here and there. If I see for some reason it is appropriate, if I see, for example, if we happen to do good number of assignments at the end, maybe 5% I would increase there. For some reason, we could not manage to give you good number of assignments for different reasons. Okay, we do for some unforeseen reasons. Then as all I would do is maybe midterm has a good amount of content at that time, I felt. So, but again, I will not take too much of a variability or uncertainty there. But at any given point of time, at the end, leave that freedom of 5% to me, which I would use with discretion. But typically, if things go as per the plan, see, just like we started with this plan, then realize now it won't work. Now we have come to a single midterm exam. This is what I would do in case there is only single exam. Any
Doesn't incorporating these machine learning algorithms to the image processing output make it a computation problem?
Not really. See, hope you remember the distinction that I tried to bring in the earlier class. When do we say something as an image processing problem? When do we say a problem as a computer vision problem? We call something as an image processing problem when your input is an image and output of your whole at the end, your algorithm is also typically giving you image as an output. That is when you call it as an image processing. When we say something as computer vision, that means it's not just image coming out as an output from your input image. it also means you are making some inferences out of that image. By that, what I mean is, let's say, image object tracking you are doing. So given in one frame an object, you are going to see where the object is next in the next frame. You are going to do face detection algorithm. You are detecting the faces. It's not just giving input as an image and getting an output as image. You are detecting those objects. Your stereo vision. Stereo vision means from two 2D images, you construct a 3D image. So you are reconstructing the 3D information there, not just in 2D image as an input and 2D image as an output. So in other words, when we say image processing, it has a set of applications. When we say computer vision, it has another set of applications. You are using machine learning to solve these image processing problems. In another case, you are using machine learning for solving the other set of computer vision problems. And of course, you might be using deep learning also for solving image processing problems, and deep learning also for solving the computer vision problems. In other words, the applications for image processing we considered versus the computer vision that we considered are different. Is that answering your question?
Yes, it's clear.
Good. Is that
But sir, in my earlier question, when I asked like how are we using machine learning, you explained that when we are classifying tumors, the benign tumor, where there we use machine learning to classify those things. So in some sense, we are inferring, right, sir? So would they still come under image processing?
no. That inference is different from what we are mentioning here. See, you are inferring about the characteristics are the pattern that distinguishes, okay, this tumor versus that tumor. One is application oriented, another is method oriented. Applications, you say image processing or computer vision based on the applications that you are dealing with. It is not in terms of how you are processing that application. Is that subtle difference clear? Otherwise, do not hesitate and do not be in a hurry to agree with me.
So it's still not clear. I think we can
Hmm.
discuss in the next slide because
Sure. Now think in these lines. Image, as I said, image processing, only set of applications we are considering, where output is also an image. You are denoising an image. You give a noisy image, output is a denoised image. You are giving an image and you are getting clusters of it. Image classification, that is image segmentation, image deblurring. These only will fall under image processing. The rest would come to computer vision. As simple as that. This is not a difficult one to comprehend.
okay, sir.
Think in these lines, okay? And how you do that processing, well, you learn something there, that is absolutely fine. It is not, this learning is not based on exactly inferring the image, but you are looking some pattern there. It is more about the pattern, finding out the pattern there. We have, yeah, maybe we will stop here then, and see you in the next class. Bye, take care.